So, good afternoon, everyone. In this afternoon, I am your instructor class. So, by the way, this is my final report, my second final in linear algebra. And by the way, I am Cristalmi Bustamante, BS Math in second year college level in GHCSC. Before I discuss, so Miss Arshel or Miss Kamaswela, can you lead the prayer? Okay, amen. Thank you. So, for this afternoon, this is our learning objectives. Yeah, can you please read Mr. Genesis Guevara? Okay, good. By the end of this topic, students will be able and expected to, since you are my students for today's class, so you will be able and expected to perform basic vector operations in R to the power of n. To write a vector as a linear combination of other vectors. To determine whether a set of vectors in a vector space V is a spanning set and linearly independent of V. And the fourth, to find the basis and the dimension of a vector space. And the last but not the least, find the null space and rank of a matrix. By the way, our lesson for today is all about the spanning sets and linear independence, which is 4.3 in linear algebra. Linear combination, a vector V in a vector space V is called a linear combination of the vectors u sub 1, u sub 2, u sub k in V if V can be written in the form which is like this: V equal to C sub 1 u sub 1 plus C sub 2 u sub 2 plus plus C sub k u sub k, which these three C's, C sub 1, C sub 2, and C sub k, which are the scalars. These are the scalars. These are the scalars. For example, 2, 3. Finding a linear combination. For vector sub 1 or V sub 1 equal to 1, 2, 3, and V sub 2 equal to 0, 1, 2, and V sub 3 is negative 1, 0, 1. To prove the steps for the proving is W equal to 1, 1, 1 is a linear combination of V sub 1, V sub 2, and V sub 3. And the second step, W equal to 1, negative 2, and 2 is not a linear combination of V sub 1, V sub 2, V sub 3. For the solution, these are the solution. W equal to C sub 1 V sub 1 plus C sub 2 V sub 2 plus C sub 3 V sub 3. Why C sub 1? Because of this 1. And C sub 2 and V sub 2 is because of V sub 1, as we can see, the second number is number 2. And C sub 3 multiplied by V sub 3 is from this number. Second step is 1, 1, 1 equal to C sub 1, 1, 2, 3 plus C sub 2, 0, 1, 2 plus C sub 3, negative 1, 0, 1 equal to C sub 1 minus C sub 3, 2 sub 1 plus C sub 2, 3 sub 1 plus 2 sub 2 plus C sub 3. And these are the solution system. C sub 1 minus C sub 3 equal to 1. And 2C sub 1 plus C sub 2 equal to 1. And 3 sub 1 plus 2C sub 2 plus C sub 3 equal to 1. And these are the matrices. These 3, 1 in the fourth column, these 3, 1 are found in this C sub 1, C sub 2, and C sub 3. Dire ni nakita, dire ni gagikan ang tulo ka 1, number 1 sa ikaupat nga column. This system has infinitely many solutions. For Gauss-Jordan elimination, this matrix will be, for this W equal to 2 V sub 1 minus 3 V sub 2 plus V sub 3. The matrix will resulted this 1, 0, negative 1, then 1, 0, 1, 2, negative 1. Then the last row 0, 0, 0, 0. For the step B, W equal to C sub 1 V sub 1 plus C sub 2 V sub 2 plus C sub 3 V sub 3. And this matrices will be resulted for the Gauss-Jordan elimination 1, 0, negative 1, 1, 0, 1, 2, negative 4, 0, 0, 0, 7. This system has no solution. Therefore, 0 is not equal 7. And then W is not equal to C sub 1 V sub 1 plus C sub 2 V sub 2 plus C sub 3 V sub 3. The span of a set. Span. The symbol of span is letter S. If the span is these sets, it is a set of vectors in a vector space V. Then, the span of S is the set of all linear combination of the vectors in S. Span for this set is all linear combinations of vectors in S. A spanning set of a vector space. If every vector in a given vector space can be written as a linear combination of vectors in a given set S, then S is called a spanning set of the vector space. Notes: span equal to V. Spans generates V, generates vector. V is spanned or generated by S, and S is a spanning set of vectors. Notes: for the notes, number 1 is span equal to 0. And the second note is, for the notes is, span is a subset of span S. And the third is A sub 1, A sub 2 subset of vectors. A sub 1 subset of S sub 2 is the span of A sub 1 is a subset of span S sub 2. For example 5, a spanning set for R third, R to the power of 3 or R cube. Show that the set S for the first vector or V sub 1, 1, 2, 3. For the second vector or V sub 2 is 0, 1, 2. And for the third vector or V sub 3 is negative 2, 0, 1. Spans R cube. For the solution, we must determine whether an arbitrary vector U in this set, vector U set, U sub 1, U sub 2, U sub 3, in R cube can be a linear combination of V sub 1, V sub 2, and V sub 3. So, U is the elimination of R cube to U equal to C sub 1 V sub 2 plus C sub 2 V sub 2 plus C sub 3 V sub 3. And the next is C sub 1 minus 2 C sub 3 equal to U sub 1. 2C sub 1 plus C sub 2 equal to U sub 2. 3C sub 1 plus 2C sub 2 plus C sub 3 equal to U sub 3. The problem thus reduces the determining whether the system is consistent for all values of U sub 1, U sub 2, and U sub 3. Therefore, the set A 3 by 3 has 3 rows and 3 columns. In the first row, 1, 0, negative 2. In the second row is 2, 1, 0. And the third row, 3, 2, 1 is not equal 0. Ax equal to b has exactly one solution for every u. Span equal to r cubed. For theorem 4.7, span is a subspace of V. If set S is this V sub 1, V sub 2, V sub k is a set of vectors in a vector space V, then span S is a subspace of V. Letter B, span S is the smallest subspace of V that contains S. Every other subspace of V that contains S must contain span S. Linear independent or Li and linear dependent or LD. S or set of S, V sub 1, V sub 2, V sub k is a set of vectors in a vector space V. C sub 1 V sub 1 plus C sub 2 V sub 2 plus plus C sub k V sub k equal to 0. If the equation has only the trivial solution C sub 1 equal to C sub 2 equal to equal to C sub k equal to 0, then S is called linearly independent. If the equation has a non-trivial solution, in other words, not all zeros, then S is called linearly dependent. What is non-trivial solution? It means has many solutions. Non-trivial. For the notes, one is linearly independent. 0 is an element of S. S is linearly dependent. V is not equal to 0. V is linearly independent. S sub 1, subset of S sub 2. S sub 1 is linearly dependent. S sub 2 is linearly dependent. If S sub 2 is linearly independent, then S sub t is linearly independent. For example 8, testing for linearly independent, determine whether the following set of vectors in R cube is linear independent or linear dependent. For set S, V sub 1, V sub 2, and V sub 3. For V sub 1 is 1, 2, 3. For V sub 2 is 0, 1, 2. For V sub 3 is negative 2, 0, 1. For the solution, C sub 1, V sub 1 plus C sub 2, V sub 2 plus C sub 3, V sub 3 equal to 0. Then C sub 1 minus 2, C sub 3 equal to 0. 2C sub 1 plus C sub 2 plus 0 since has no variable or numbers, so it is 0, equal to 0. 3C sub 1 plus 2C sub 2 plus C sub 3 equal to 0. For this matrix, 3 by 4 has 3 rows and 4 columns. 1, 0, negative 2, 0, 2, 1, 0, 0, 3, 2, 1, 0. It will be resulted, or if we will use the Gauss-Jordan elimination, this will be the answer. 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0. Has leading 1 and below has zeros. C sub 1 equal to C sub 2 equal to C sub 3 equal to 0, only the trivial solution. Then S is linearly independent. Example 9, testing for linearly independent, determine whether the following set of vectors in P sub 2 is linearly independent or linear dependent. For set S, this 1 plus x minus 2x sub 2, 2x squared is the first vector or V sub 1, and then 2 plus 5x minus x squared for the second vector or the V sub 2, and then x plus x squared is the third vector or V sub 3. Then the solution is C sub 1, V sub 1 plus C sub 2, V sub 2 plus C sub 3, V sub 3 equal to 0. For other solution is this. For C sub 1, 1 plus x minus 2x squared plus C sub 2 multiplied by 2 plus 5x minus x squared plus C sub 3 multiplied by x plus x squared equal to 0 plus 0x plus 0x squared. Oh my god. For the solution system is C sub 1 plus 2C sub 2 equal to 0. Then C sub 1 plus 5C sub 2 plus C sub 3 equal to 0. Negative 2 C sub 1 minus C sub 2 plus C sub 3 equal to 0. To make this as a matrix, this will be like this: 1 2 0 0 1 5 1 0, -2 -1 1 0. For this matrix, if we use the Gauss-Jordan elimination, this will be the answer: 1 2 0 0 1 1 1/3 0 0 0 0 0 has leading 1. This system has infinitely many solutions. This is non-trivial. If we say many solutions, so this is a non-trivial solution. S is linearly independent. For example, C sub 1 equal to 2, C sub 2 equal to -1, and C sub 3 equal to 3. Example 10. Testing for linearly independent. Determine whether the following set of vectors in 2 by 2 matrix space in linearly independent or linearly dependent. For set S, 2 1 0 1. This is the V sub 1 or the first vector. 2 by 2 matrix space. And the second vector or V sub 2 is 3 0 2 1. For the third vector or V sub 3, 1 0 2 0. For the solution, C sub 1 V sub 1 plus C sub 2 V sub 2 plus C sub 3 V sub 3 equal to 0. And then C sub 1 and rewrite the first vector plus C sub 2 multiplied by the second vector. Rewrite the second vector which are 3 0 2 1 plus C sub 3 multiplied by the third vector or V sub 3, and this will be resulted 2 by 2 matrix space 0 0 0 0. Then 2C sub 1 plus 3C sub 2 plus C sub 3 equal to 0. C sub 1 plus 0 equal to 0. 0 plus 2C sub 2 plus 2C sub 3 equal to 0. Then C sub 1 plus C sub 2 plus 0 equal to 0. And this will be the matrix. 4 by 4 matrix. And it resulted as the Gauss-Jordan elimination has leading 1 and below has zeros. C sub 1 equal to C sub 2 equal to C sub 3 equal to 0. This system has only the trivial solution. S is linearly independent. The spanning set is linearly independent. Theorem 4.8, a property of linearly dependent sets. A set of S V sub 1, V sub 2, ... V sub k, for k is greater than or equal to 2 is linearly independent if and only if at least one of the vectors V sub j in S can be written as a linear combination of the other vectors in S. For the proof, C sub 1 V sub 1 plus C sub 2 V sub 2 plus plus C sub k V sub k equal to 0. Therefore, the spanning set is linearly dependent. For C sub I is not equal to 0 for some I. For this one, v sub I equal to c sub 1 over c sub 1 multiplied by v sub 1 plus dot 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 c sub I minus 1 over c sub I multiplied by v sub I minus 1 plus c sub I plus 1 over c sub I multiplied by v sub I plus 1 plus dot 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 plus c sub k over c sub I multiplied by v sub k, and this will be resulted. Let v sub I equal to d sub 1 multiplied by v sub 1 plus dot 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 plus d sub I minus 1 multiplied by v sub I minus 1 plus d sub I plus 1 multiplied by v sub I plus 1 plus dot 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 plus d sub k multiplied by v sub k. Then d sub I v sub 1 d sub 1 plus d sub 1 v sub 1 plus dot 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 plus d sub I minus 1 multiplied by v sub I minus 1 minus v sub I plus d sub I plus 1 multiplied by v sub I plus 1 plus dot 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 plus d sub k multiplied by v sub k equal to 0. Then c sub I equal to d sub 1 dot dot dot. Then c sub I minus 1 equal to d sub I minus 1. C sub I equal to negative 1. C sub I plus 1 is equal to d sub I plus 1. And c sub k equal to d sub k. This is a non-trivial solution. It has many solutions. So the spanning set is linearly dependent. Corollary to theorem 4.8. Two vectors u and v in a vector space V are linearly dependent if and only if one is a scalar multiple of the other. And that's all in this afternoon class. That's all, and thank you so much for listening my report. Thank you guys. Goodbye.